Welcome back to Algorithmic Game Theory. Great that you're still here. What did we do so far? Well, we introduced congestion games and we showed that there is always a pure Nash equilibrium in every congestion game. Today we'll generalize the class of games that we consider towards what is called normal form games. And we'll also generalize the notion of a pure Nash equilibrium. But then, as we will see, not always a pure Nash equilibrium exists. But what we will show next time is that always a mixed Nash equilibrium exists. But before we get to that, let's first introduce the more general notion of a game, a so-called normal form game. So what is a normal form game? Let's define this formally. We say that a normal form cost minimization game is a triple which consists of N, Si, and Ci. What are these? Well, we'll have N as the set of players. We'll usually call the number of players N and often just write as the players the set of 1 through N. And for each player, we now have the set Si, which is the set of pure strategies of that player. And we'll call the Cartesian product of all these the set of states or pure states or strategy profiles or pure strategy profiles. So this should feel somewhat familiar. N as a set of players we also had in the context of congestion games, and we also had a set of strategies for each player. The notation is a little different now, and I'm just sticking to standard notation here, which may be a little unfortunate from time to time because now capital SI is the set of all strategies, whereas in the congestion games we called this set of pure strategies sigma I, and capital SI was an element of this set of pure strategies. So this will be consistently inconsistent throughout this class, and I apologize for this in advance. This is the standard notation that we will use for these normal form games, or often we might just call them games. And then we again have this Cartesian product of all strategy spaces, which is the set of states, or as we also want to call them, just strategy profiles or pure strategy profiles. So these are all called pure strategies to distinguish them from mixed strategies, which we will see later in this class. Good. Now all of the players choose one of these strategies, and this means that players incur certain costs. And we write this as follows. So for each player, we'll have now CI as a function mapping from S to the reals. This is the cost function of player I. So we take as the input a a strategy profile, a profile of pure strategies, and then this maps to a cost that this player is incurring. Alternatively, you could also define this as a payoff or a utility that the player wants to maximize. That's actually sometimes more convenient, and we'll switch between the two throughout this class, but for today we'll only talk about cost minimization. Good. So we can actually capture congestion games in here. How can we do that? Well, as I was saying, SI will be again the strategies, which were in the context of congestion games, were just subsets of the resources. And the cost functions, well, those had a particular structure in the context of congestion games. But now those may be just arbitrary functions. So they are not these underlying resources and delay functions, which were exactly the ones that induced this structure in the cost functions of congestion games. How can we define other such normal form games? Well, what we can do, for example, is a bimatrix game. In a bimatrix game, we'll have always two players. So this means nothing but that n is equal to 2. And now the strategy sets are just something. We don't actually care. And the cost functions are now described in terms of matrices. We'll now have two matrices. A and B, which fully describe the cost function. Here now you have to be a little careful, because there's now small s's, which are strategy, and there's capital s's, which are the strategy sets. But usually it's just clear from the context which means which, that this should be a small s because it is contained in the capital S, in the capital SI. Good. Now we have these two matrices, and how does this now induce a game? Well, one player, player 1, chooses a row of these matrices, and player 2 chooses a column in these matrices. And then the cost is defined as the entry at which we end up. So more formally, player 1 is the row player, and player 2 is the column player. and we'll have that C1 of S is equal to A subscript S1 comma S2, and C2 of S is equal to B of S1 S2. Let's see this in action. Let's consider a typical congestion game with only 2 players. So we'll have maybe a source here, have 2 intermediate vertices and a sink, and there are delay functions. This is how we would write this as a congestion game. But we can also write this as a normal form game, and more precisely we can also write this as such a bimatrix game by now writing down 2 matrices. The usual notation is not to write 2 separate matrices, but rather to write all of this in one large table. What are the possible strategies of the 2 players? Well, both players actually have 3 possible strategies in this game. Namely, player 1 can, for example, use the top path, or they can use the zigzag path, or they can use the bottom path. And the same is true for player 2. Player 2, because this is a symmetric game, both players want to get from the source to the same sink, they both have the same choice of strategies. So my second player will now be blue, and I'm also writing down just the same strategies here. Okay. Now what do I write in these cells in this table? In these cells of the table, I always write 2 numbers, one on the bottom left and one on the top right. In the top right, you'll see this is the cost that the column player will incur, and the bottom left, this is the cost that the row player will incur. So if, for example, the row player chooses to choose the top path and the column player chooses to choose the top path, then what's the delay? The delay will be 2 plus 8 for each of them. So both of them will incur a cost of 10. Great. Let's see how we fill the rest of the table. What if, for example, the row player uses this zigzag path and the column player uses the top path? Then there will be 2 players on this edge and 1 player on this edge, 1 player on this edge and 1 player on this edge. So what will the costs be? For the zigzag path, the cost will be 2 plus 5 plus 9. So we'll get 2 plus 5 plus 9, 16. And for the column player, well, that's now 2 plus 7, so that's 9. And let's do one more example. Let's see what we have to fill in here. Well, we used these two bottom edges here. So this will be 3 plus 9, because the other player isn't using these. This is 12, 3 plus 9. And then there's also the choice of the column player. This will be a cost of 1 plus 7. So this will be 8. And now this way you can just fill out the entire table. You'll get 16 and 9 up here. You'll get 18 and 18 here. You get 16 and 13 here. You'll get 12 and 8, 13 and 16 and 14 and 14. And once again, now there is one player who chooses a row, one other player who chooses the column, and then we'll have the two entries which indicate us what their costs will be. Mathematically, these are actually two matrices, one for the row player, which we called A, and one for the column player, which we call B. And the red numbers, those are matrix A. The blue numbers are matrix B. But this is not the only way you can construct a bimatrix game. So this does not necessarily have to be a congestion game. You can also take other games in here. And let's see another example. This game here is called Battle of the Sexes. There is a traditional, very sexist explanation of what is happening here, but let's just be a little more 21st century and let's just assume there's person A who wants to go to the movies and person B who wants to go to the movies, and they actually want to go together. Both of them have a favorite movie, but unfortunately it's not the same. But it's more important for them to go to the movies together than apart. How does this look in this matrix? Well, we see generally the row player has the smallest cost if both players choose strategy B. So the row player would actually prefer that both players go to movie B. But both players going to movie A, that's a little worse, but it's definitely better than one of them going to A and the other one going to B. For the column player, we have something very similar. The column player prefers that both of them go to movie A. Both of them going to movie B is also fine. Well, one of them going to A, the other one going to B, that has a higher cost. So you see that many situations in which you have strategic behavior and somehow mismatched preferences, you can indeed capture in such a table. But what we now have to do is we'll have to actually model the strategic behavior. And for this, we'll generalize the notion of pure Nash equilibria and see, does there exist a pure Nash equilibrium in this game or not? So let's first generalize the notion of a pure Nash equilibrium. A pure Nash equilibrium, I hope you remember from the congestion games, is a state or a choice of pure strategies for all players such that no player wants to unilaterally deviate, which means that no player can decrease his or her cost by unilateral deviation. How do we now generalize this to these normal form games? Well, we actually just have to copy the exact definition. We say that a strategy SI is called a best response for player I against a collection of strategies S minus I if the cost of this strategy is at most the cost of any other strategy. So only the notation is a little different, the meaning is just the same. We'll have a strategy SI, which we call a best response against what the other players are doing, if, well, no other strategy is actually better for this player. And now a pure Nash equilibrium is a state or strategy profile such that for all players SI is a best response against S minus I. So exactly the same thing as in the context of congestion games, we'll have a state or a choice of pure strategies for all players, such that no player will benefit from unilateral deviation, which means no player can decrease his or her cost by moving to another strategy. Let's see this in our example of Battle of the Sexes. Are there pure Nash equilibria in here? Maybe. Let's first talk about best responses. What are best responses here? Well, this is exactly what I was trying to say before. Now, one player is doing something and the other player is reacting to this. What is the best response? Or, well, there might even be multiple best responses. Not in this game, but generally there might be. If the row player is choosing A, what does the column player want to do? Well, the column player also wants to do A. So let's mark this in here. If the row player is choosing B, then the column player also wants to choose B. Because, well, 2 is smaller than 5, but here 1 is smaller than 6. So these are best responses. Now let's do the same thing for the row player, fixing the column player. If the column player is playing A, then the row player also wants to play A. And if the column player is playing B, then also the row player wants to play B. So I've now marked the best responses in this table. And what we see is there are these two cells in which both players are playing a best response. And this means those are pure Nash equilibrium. That's nice, but what about other games? Do we always have the structure that there is a pure Nash equilibrium? Well, unfortunately not. And it's maybe not a surprise how, because if we had, for example, a 7 here, then this wouldn't be a best response anymore for the column player, because then the column player would want to move to B. And then we would change the 2 here, for example, to 6, then also the column player would want to have a different choice there. So it's kind of easy to destroy this example. And let's see another example of a biomatrix game in which there is actually no pure Nash equilibrium. This game is called Inspection Game. Again, we have 2 players and both players have 2 strategies. What are the 2 players? Well, one of them is a train traveler and the other one is a ticket inspector. The row player is the inspector and the column player is the traveler. What choices do these players have? Well, the column player, the train traveler, can either buy a ticket or not. And this we now say means comply. Comply means buying a ticket. Defect means not buying a ticket. And the ticket inspector can choose to be either lazy or may choose to actually inspect the ticket. The point is now, well, if you know that the train, and how we do now fill this table? okay, if I buy a ticket, then I buy the ticket. I just have the cost of buying the ticket. So let's say this is 15 euros. And I pay this regardless of whether my ticket gets inspected or not. But if I don't buy a ticket, then, well, if nobody checks whether I have a ticket, then my cost will be 0. But if somebody does inspect and I don't have a ticket, then my cost will be 60 euros. Okay, this is the choice that the train traveler has. And let's now try to capture what choice the inspector has. Well, they can either decide to be lazy or to inspect. And let's say, okay, if the traveler does have a ticket, then of course being lazy doesn't have any cost, whereas inspecting the ticket, okay, this has a small cost of me because it takes just some effort to inspect the ticket. Whereas if the traveler does not have a ticket and I inspect the ticket, then if I'm lazy, then I'm losing money. As opposed to if I inspect the ticket, well, it still takes some work for me, but it's at least worth it because I'm getting some reward of this. Maybe I'm compensated for the company that I work, that I found somebody who didn't have a ticket and I actually found this out. What are best responses here? Well, this is maybe not a surprise for you. If you've ever taken a train, then if you knew what the inspector would do, you would definitely, well, do the respective thing. If you know that your ticket will be inspected, then you'll certainly buy a ticket. If you know that your ticket will certainly not be inspected, then you wouldn't buy a ticket. Well, maybe not you, very honest audience, but if we just consider a very strategic agent, why would you buy a ticket if you know that never anybody actually cared? And let's see this here also in this table. If we know that the inspector is lazy, then defecting is the best response. Whereas if we know that the inspector is indeed inspecting, then complying, so buying the ticket, is the best response. Now, let's think about the perspective of the inspector. What would we do? Well, if everybody has a ticket, there's really no point in inspecting. So, let's be lazy. But if the player certainly doesn't have a ticket, then we should certainly inspect. What do we see here? Well, none of these cells corresponds to pure Nash equilibrium. Maybe not a real surprise at this point, because there is no state in which both players are playing a best response. So this brings us to the question, what will happen instead? And if you realize what happens in reality is that, well, sometimes people do buy tickets, sometimes they don't. Sometimes tickets get inspected, sometimes they don't. So there is some inherent, maybe, randomization of what will actually happen. And this is indeed captured by what is called a mixed Nash equilibrium, which we'll introduce next. As we've seen in our inspection game, a pure Nash equilibrium doesn't always exist. But as it will turn out, as we will show next time, a mixed Nash equilibrium always exists. What is this? Well, in a mixed Nash equilibrium, players don't just choose one strategy, but they choose a probability distribution over strategies. This is what we call a mixed strategy. So a mixed strategy which we will call small sigma I for player I is a probability distribution over Si, the set of pure strategies. Actually, we'll only consider this in the context of finitely many pure strategies and finitely many players, in which case, well, the notion of probability distributions are much easier than in the much more general case if you had like infinitely many strategies. So we can now write down a mixed strategy as a vector sigma I comma Si. So these are the entries of this vector. And the entries in this vector sum up to 1. So sigma I comma Si, this is the probability that player I plays strategy Si. And now we'll have a mixed strategy profile. So we'll take a mixed strategy for each of the players and we'll now associate also a cost to such a mixed strategy profile. Like we did this for pure strategies, we may now call this sigma without any subscript. This is the vector of all sigma I, where we now give a mixed strategy to each of the players. And the cost of player I in sigma, how do we get this? Well, this is exactly what we would have as the expected cost if player 1 draws a strategy from sigma 1 up to player n drawing a strategy from sigma n, and then we'll consider the cost that player I would incur. So all of the players draw independently a strategy, and now we'll evaluate the cost of the pure strategy profile that we are reaching this way, and let's now consider the expectation of this. So alternatively, we can also write this. If we write out this expectation, take the sum over all strategies for all players. And now, what is the probability that player 1 plays S1 up to the probe times and so on, and the probability that player n plays Sn, and then we'll multiply this with the cost that player I incurs in state S. Good. So what we can also do is we can represent every pure strategy as such a mixed strategy. So any pure strategy can be represented as a mixed strategy. How that? Well, very easily. You set sigma I, si to 1 for one si, and sigma I, si prime equal to 0 for all si prime which are not si. What does this mean? Well, effectively now we have a larger strategy space. Beyond the pure strategies, we now also have mixed strategies. And for these mixed strategies, we can now just consider the exact same notions of best responses and of equilibria. And the equilibria, or if all players are playing such a best response, this is what we call a mixed strategy, mixed Nash equilibrium. Let's write this down. A mixed strategy sigma I is a mixed best response and let's say against sigma minus I if the cost that I incur if I play this strategy is no larger than if I played any other mixed strategy. And a mixed strategy profile is called a mixed Nash equilibrium. If sigma I is a best response against sigma minus I for all players. So nothing has changed up to this point because we just broadened the set of strategies, and now we say, okay, rather than only allowing you to choose a pure strategy, we allow everybody to choose a mixed strategy, and on these we again define best responses the exact same way. And also equilibria, these are now called mixed Nash equilibria because, well, the strategies are now mixed strategies. The interesting thing is that actually it is now enough to consider deviations to only pure strategies. So we now defined this here in a way that we said, okay, you shouldn't want to play any other mixed strategy instead. But the following lemma tells us that we actually only have to compare this mixed strategy to any pure strategy. And this lemma says that a mixed strategy is a best response against some sigma minus I. Okay, we want to call this sigma I the strategy. If and only if we have that the cost of playing sigma I against sigma minus I is at most the cost of playing Si prime against sigma minus I for all pure strategies Si prime. So compare this to the definition of a best response. There we said, okay, this we have to compare this to any possible mixed strategy. Now we're saying, okay, we don't actually care too much about all mixed strategies. All we have to care about is all possible pure strategies. So the player only deviates to a pure strategy, and we ask, how much are we gaining anything by moving to such a pure strategy? Let's prove this. And the only if part here, this is very trivial indeed. Because the only if part tells us that, well, we only have a mixed strategy, we only have a best response if we wouldn't want to deviate to any pure strategy, to any other pure strategy. But this was already included in the definition, because every possible Si prime is also a possible sigma I prime. The if part, this is more interesting. We want to now show that if this is fulfilled, then actually we have, if this condition is fulfilled, then we have a best response. And by proving this, we see, okay, by proving this, we see actually a proof technique that we will repeatedly now use. Namely, well, if we have this, then so all that remains now to show is this if part, which means that if this condition here is fulfilled, then we have a best response, also in the sense that, as we defined this before, that you wouldn't want to use any mixed strategy. And this is very crucial to understand this, that actually mixed strategies cannot be any better than the pure strategies they are composed of. Let's write this down. We let sigma minus I be any mixed strategy profile for the other players. And we let sigma I be a strategy such that Ci of sigma I, sigma minus I is at most Ci of Si prime, sigma minus I for all Si prime in Si. Now let's consider any other mixed strategy. Which I want to call sigma I prime. What's now the expected cost that we get if we play sigma I and the other players keep playing sigma minus I? This is now, we can now write this expectation as follows. We can write this as the probability that we play Si prime for every possible Si prime, and then multiply this with the expected cost of Si prime, while the other players are still randomly drawn from sigma minus I. Here, for this step, it is actually crucial that the other players are doing something independent of what we are doing. We now being player I. Because this means we can actually totally separate this. We can just say, okay, we now let the other players just do their randomization. We draw something from our distribution, and only then we combine this. So this is the expected cost if we are definitely playing Si prime. So let's first just draw Si prime, and only then the other players draw something where we are definitely doing this Si prime. Now what is this here? At least, well, this is at least the minimum of all these Si prime. Because any probability distribution over any numbers in expectation cannot give you something that is smaller than the minimum that we will ever see. Or in other words, this is somehow a weighted average. And the weighted average of any numbers cannot be any larger than their minimum, cannot be any smaller than their minimum. And what do we know about this minimum? Well, this minimum is, by our assumption, at least Ci of sigma I, sigma minus I, because this was exactly what we were assuming here, that this holds for any Si prime. So in particular, this also holds for the minimum. And this means now that the cost when we deviate to sigma I prime, this will be at least the cost if we deviate to sigma I. Having now another look at this lemma, let's once again understand what we're proving here. This means now that for a strategy to be a mixed best response, it is enough to see whether no other pure strategy gives us something better. And this is actually important because it doesn't actually matter whether we talk about mixed best responses or pure best responses. Those are exactly the same thing. A strategy is generally a best response if there is no pure strategy that will give you something better. And why is this important? Well, this means that if we understand a pure Nash equilibrium also as, well, a choice of mixed strategies, then because of this lemma, it is also a mixed strategy, a mixed Nash equilibrium. Because, well, a pure Nash equilibrium certainly fulfills this property, and all this now means that it is also a mixed Nash equilibrium in the way we defined this just a moment ago. But there are more tools to actually understand these mixed Nash equilibria, one of which we will prove next. How can we find a mixed Nash equilibrium? This isn't entirely trivial because we have to have these mixed strategies which are best responses. But now we will characterize what it actually means for a mixed strategy to be a best response, and this will then be extremely helpful when we actually find a mixed Nash equilibrium. And what is this property? Well, it is that any mixed best response is actually a probability distribution over pure best responses. Formalized in this following lemma, a mixed strategy sigma I is a best response against sigma minus I if and only if for every strategy in the support of sigma I which means every Sj in Si that gets a non-negative probability mass, non-zero probability, if every such strategy in the support is a best response against sigma minus I. Let's digest this. A mixed strategy, we now ask, well, is this now a best response? And what this lemma claims is that all we have to see is whether every strategy that we're now playing with a positive probability, so with a non-zero probability, this also has to be a best response at this point in time. So this limits our choice of distributions drastically, because all we can actually do is we can see at some point, well, there are multiple best responses, and we now take just a probability distribution over all these pure best responses. The proof of this is actually pretty similar to the lemma that we proved before. So this is again an if and only if. Let's first assume that we have a probability distribution over pure best responses. And we want to show that this fulfills the property of also being a best response itself. So this means that this is the if part. So we consider any distribution sigma I over best responses. Then we have that take any other pure strategy. How big is now the cost that we incur if we play sigma I? Well, we can once again write this as take the sum over all strategies, the probability that we play this strategy, times the cost that we incur if we definitely play Si and the others play sigma minus I. Now what we assumed was that everything that has a positive probability mass is actually a best response. So this means that this can be no larger than if instead of playing Si, we would play Si prime. Because, well, either Si is a best response, in which case this here is at most this much, or this thing here is 0, in which case, well, we don't care about how large this Ci term is. And now the important thing is, well, these things here, these sigma I comma Si, they sum up to 1. The Ci is now independent of Si, so this is exactly Ci of Si prime comma sigma minus I. And this means we'll have a best response here, because whatever other pure strategy we're considering, we cannot gain anything. This is exactly what we proved in the previous lemma, that to be enough for a mixed strategy to be a best response. Good. Now there's the other half. Let's now assume that we do not have a distribution over best responses. Then we want to show, well, this strategy that we're currently playing, this isn't a best response either. So this is actually for the only if part. We can now do the following. We can say consider any distribution sigma I, which is not a distribution over best responses. This means that we'll have one strategy which gets a positive probability, but which is not a best response. So that is there are Si and Si prime such that Ci of Si comma sigma minus I is bigger than Ci of Si prime comma sigma minus I, but at the same time Si gets a positive probability. So once again, we don't have a probability distribution which is only over best responses. This means that there has to be one strategy, which we call here SI, which is not a best response, which we still gets positive probability, but there is another strategy SI prime, all pure strategies here, which would have a strictly smaller cost. How could we now improve our response? Well, we can just shift all probability mass from SI to SI prime, and this will certainly decrease our cost. So now construct sigma I prime from sigma I by decreasing sigma I comma Si and increasing sigma I comma Si prime. And more precisely, the new sigma I comma Si should be 0. Or it doesn't actually matter, but we can move this as much as we like. Even actually any change is already enough. And then we'll have that Ci of sigma I prime comma sigma minus I is smaller than Ci of sigma I comma sigma minus I. Why that? Because whenever we were playing Si before, we are now playing Si prime. Si prime has a smaller cost and everything else didn't change, so the overall cost must have reduced. This means that sigma I cannot be a best response. Now let's combine these insights to actually find a mixed Nash equilibrium for this inspection game. Because we now have an understanding of what it means to be a best response, of what it means for a mixed strategy to be a best response. How do we do this in more detail? Well, we'll now assign probabilities to lazy and inspect, as well as comply in defect, so that actually both players don't actually care what strategies they are playing. Why that? Because here in this 2x2 game, actually a pure strategy, a pure best response is something pretty easy that you don't want to actually move to the other strategy. And it is actually important at this point to realize, well, if one of the two players plays something deterministically, so if they put only a probability mass of 1 on one of the strategies and 0 on the others, this will never be a mixed Nash equilibrium. Why that? Because, well, if you know that your ticket doesn't get inspected, then most certainly you won't buy a ticket if you're strategic and selfish. Good. Let's see this now. We'll have a probability of 1 minus p on being lazy and on p on being on inspecting, and we have a probability of 1 minus q on complying and a probability of q on defecting. And we'll have that P and Q are both in the open interval between 0 and 1, because as I was saying, if they are taking the extremes, then the other party knows exactly what they are doing, and this won't make them, will never make them happy. This, however, that this P and Q are neither 0 nor 1 means that both players are putting probability on both of their strategies. And this means that both strategies have to be best responses. This means nothing but for two strategies to be both best responses, they both have to have the same cost. Let's see this for the row player, what this means. Well, for the row player, we'll now have that the cost of being lazy against this 1 minus q, q strategy, this has to be exactly the same as the cost of being of inspecting against this q 1 minus q, q strategy. And how do we now calculate these? Well, this is very straightforward because the expected cost, if you're lazy, this will be 1 minus q times 0 plus 10 times q. Right? Because the column player is complying with probability 1 minus q and is defecting with probability q. Let's do the same thing for the other side. We'll now have that the expected cost of inspecting is 1 if the other player is complying, and it is 6 if the other player is defecting. And those have to be the same. So we now have that 10 times q is equal to 1 minus q plus 6 times q. So what we get from this is that q is equal to a fifth. Once again, where was this coming from? This was coming from the fact that for the inspector doesn't, or for the inspector, both being lazy and inspecting have to be both best responses. And this is why we had this equality here. So this is what we're then deriving for the probability Q, which is, interestingly enough, the probability mix for the column player, for the traveler. We can do the same thing for the column player. What's the expected cost of complying? This will have to be the same as the expected cost of defecting. What's this here on the left hand side? What's the expected cost of complying? The expected cost of complying is 15 regardless of what the other player is doing. So it's 15 times 1 minus p plus 15 times p. And for the column, for defecting, what's the cost there? Well, if we don't buy a ticket and we don't get inspected, this happens with probability 1 minus p. We'll have to pay 0. And if we do have a ticket, if we do get inspected and don't have a ticket, then our cost will be 60. So what we're getting from this here is that P has to be a quarter. So we now did the same argument also for the traveler. For the traveler in our mixed Nash equilibrium, both of these strategies have to be best responses. And this means that the row player has to be choosing this probability P so that actually the player doesn't care, so that the expected cost of complying and defecting will be the same. And this is now what we got from this. We now found that for Q being a fifth and P being a quarter, both these inequalities are true. This means that we would now set a probability of 3/4 on complying, we would set a probability of 4/5 on complying and 1/5 on defecting, and a probability of 3/4 on being lazy, and a probability of 1/4 on inspecting. And what is now actually interesting here, at least from my point of view, is that because the cost that if you're caught and you don't have a ticket is pretty high, you actually always want to buy a ticket, or kind of always want to buy a ticket. So although the inspector is lazy most of the time. There's also another more visual way to interpret what is happening here, because we can also draw the cost of the row player depending on what strategy they choose. What will be the cost of the row player? Well, the cost of the row player, this now depends on the probability Q that the column player is putting on the entries. Now, what can happen? Well, the probability can be 0. Maybe let's quickly go back. So Q can be 0. What does this mean? If Q is 0, then we're always complying. This means for the row player that there is a cost of 0 for one strategy and a cost of 1 for the other strategy. So this we see here. If Q is 0, then we'll have a cost of 0 for one strategy and a cost of 1 for the other strategy. Whereas if Q is 1, this means that the traveler definitely does not have a ticket. Then what we see in our table is a cost of 6 and a cost of 10 respectively. And we can now connect these lines. So the top line is the cost of being lazy, the bottom line is the cost of inspecting. And here now, there is a point at which the two intersect. And this is exactly the point Q at which I'm indifferent between being lazy and inspecting. So if the row player is now, if the column player is now defecting with a probability exactly equal to this much, then suddenly I'm indifferent between being lazy and inspecting. And we can do something very similar for the column player. Here now we draw the respective P, and the column player had the choice of buying a ticket. If we buy a ticket, then our cost is 15 regardless of whether we are inspected or not. And there is the cost of not buying a ticket, which will be 60 or 0. And again, we have this point P at which the two lines intersect. And so also visually, we found the equilibrium by only drawing these lines, which is exactly the kind of equations that we were solving. Once again, this was the comply and this was the defect strategy. So you may now ask, is this really what people are doing in reality? Is it really that they are coming to the train station, flipping a coin and deciding, well, today I buy a ticket, today I don't buy a ticket? Maybe it is not. And probably it's also not that the inspectors are truly lazy or they are even flipping a coin whether they are lazy today or not. But maybe it's more like, well, 80% of the people buy tickets and 20% of the people don't. And on, well, 75% of the trains there is no inspector, and only on 25% of the trains there is an inspector. And in this case, you're just happy with your choice, regardless of whether you belong to the group of people who buy tickets or who don't, because it turns out either of the two options will give you the same expected cost. So you can rather think of a mixed Nash equilibrium as a large population of players for every player in our sense, and then they are just randomly matched. And just because you don't know who you will be playing with in advance, you are just happy with your choice. And you always play the same thing, actually. Cool. So this completes our introduction of mixed Nash equilibria. Next time we'll talk about the question, do they always exist? And yes, the nice answer is they do always exist. Unless there are infinitely many players or a player has infinitely many strategies, in which case they might not exist. But for the examples as we were considering them today, there is always a mixed Nash equilibrium, and this is what we'll prove next time. Thank you very much for your time for today. If you have any questions, feel free to let me know, and have a nice day. Bye.